and supposedly everybody can hear me. So just to make sure, if you can't, let's talk about the way we'll go do some procedures. If you have any technical issues, you can chat with the host in the chat box. And what I'd like to do, since we've got over 30 folks here, is we use the Q&A box for questions and answers. So if you have a question, comment, whatever, as we move along, simply type it into the Q&A, and I generally get a notification on my screen that something has come in, and I will click on that. If by any chance I miss somebody adding a question or whatever, if it goes for a minute or two where you've not heard a response from me, then don't hesitate to unmute and say, Roger, I typed a question for you, and I will then go to the Q&A and see what we've got. Otherwise, if there's any technical difficulty with sound or whatever, please type that in the chat box, and our host will deal with you directly on that. And if it's something that's of interest to everybody, I'm sure that he'll let us all know so we can do whatever we need to do. So today we are going to talk about Department of energy storage technologies for solar and wind power. This is the United States Department of Energy, but believe me, there's plenty of other energy groups around the world who are asking the same questions and coming up with most of the same answers. So whatever we talk about here is with numbers from the United States, multiply that by about 5, and then that gives you some idea of what's happening around the rest of the world. So I'm not, don't, by the way, nobody's going to walk out of here today with good enough knowledge to design a 100 megawatt, 129 megawatt hour storage system. Okay, but you're going to have a pretty good idea what's out there. And sometimes, I know in my case, I sometimes get so involved with my day-to-day activity that I don't get a chance to look beyond that horizon. And we're going to try to look behind that horizon and beyond that horizon today, and imagine where we might be 10 or 15 years from now. Okay, so let's move on, and let's look at some of the things we might want to talk. We're talking about energy storage. So how do you store energy? Well, you might do it one of these ways. You've got MGH, that typical mechanical potential energy. Lift something up, it falls back down again, you can get the energy back, or at least some of it. Half I omega squared. Rotate something fast enough with a big enough moment of inertia, you can store quite a few joules of energy in kilowatt hours, whatever. Everybody knows the half mv squared formula. If you've got an electric car, you use it every day you drive it, because every time you do regenerative braking, you are recovering some of that energy that you have developed in the process of getting up to 120 miles an hour. The electrical engineers will remember the half CV squared, the way you store energy in a capacitor or in a magnetic field in an inductor, for the half Li squared. And then there's one left that we haven't talked about, and it's probably the most important of all. The energy we're getting from the sun, of course, that's Einstein's formula, and indeed it's the fusion reaction from the sun that's enabling a lot of things that are going on. So let's move on, and first of all, we should give credit to how this first got started about 4 or 5 years ago. Someone discovered this study that had been done by the National Renewable Energy Labs in 2012. So we're now able to look today where we stand 10 years later compared to what their goals were, and we'll look at what their goals were in just a minute. Actually, what they were trying to determine is whether we could have 80% of our energy be produced by renewable sources by the year 2050. And as of 2022, we find that we can do 100% even sooner than that if we play our cards right. So, but this is how some of the ball got started rolling here back in 2012. As you look through the slides, the REFS means Renewable Energy Futures Study, but there will be a number of additional references from things that have been happening since 2012. Okay, so from a mechanical perspective, first of all, I'm not sure that everybody knows that 1 kilowatt hour is 2,655,000 foot-pounds. And so if you can convert at 100% efficiency and you weigh 2,655,000 pounds, you only have to climb 1 foot in order to create a 1 kilowatt hour of potential energy. But if you weigh less than 2,655,000 pounds, then you're going to have to climb a little higher in order to store up that amount of potential energy. For example, if you were a cubic foot of water, you'd weigh 62.5 pounds. And therefore, if you take 425 of these cubic feet of water, and if you lift them 100 feet, then that gives you 1 kilowatt hour of potential energy. All right, just trying to put this whole problem into perspective here. If we let this 425 cubic feet of water come back downhill again and allow it to come down at a regular rate and give it 1 hour to fall down, then that would be 425 over 60 minutes or whatever. In any case, that's the equivalent of 1 kilowatt, because if you divide a kilowatt hour by an hour, then that's 1 kilowatt. And as you know, that's about what it takes to run a 1 horsepower motor. A cubic foot of concrete is 150 pounds. So if you take 177 cubic feet of concrete and lift it 100 feet, then you have expended a kilowatt hour of energy and have created a kilowatt hour of potential energy, not counting losses in the system. So if you want to save energy mechanically by lifting weights or water or whatever, these are some numbers that come in handy when you do your system design. Knowing that a horsepower is 550 foot-pounds per second or 746 watts, 100% efficiency that is, then we recognize about 1,000 watts will give you 1,000 watts in gives you about a horsepower out, depending on how efficient your motor is. Okay, so again, just to get an idea of how much that hydroelectric energy it takes to keep a horsepower motor running, now everybody knows. Okay, then there's the thermal part of a kilowatt hour is 3,413 BTUs. And if you look at a gallon of gasoline, it has about 120,000 BTUs in it, which would be 35 kilowatt hours. Of course, if you can convert it at 100% efficiency, and you can't do that. If you burn it, if you're lucky, you get 30% and variable rates that you burn it in an automobile. But in any case, and in terms of basic energy, gallon of gas is about 35 kilowatt hours. And let's say that you're going to fill your vehicle and at a gas station at a rate of about 6 gallons a minute. Well, then that equates in terms of energy to 210 kilowatt hours per minute. And if you do that for an hour, you will have dumped 12,600 kilowatts into your tank, or 12.6 megawatts. So effectively, it takes 12.6 megawatts is what your rate of filling your gas tank is. And it's kind of a mind-blowing number, but it kind of explains why it takes a little while longer to fill an electric vehicle. Okay, so what have I done? I guess I clicked my clicker accidentally. So if you're going 60 miles an hour at 30 miles a gallon, that's 2 gallons per hour, 70 kilowatt hours per hour, but that's heat plus motion. The motion part of that is only about 30% of that, or 21 kilowatt hours per hour, or 21 kilowatts. So again, just some numbers for you to play with. I'm sure that at dinner tonight, you'll want to have something technical to talk about, as most other engineers and architects do. It's the way we bore everybody to death so that they get on and eat their meal. In any case, kilowatt hour will heat 10 gallons of water from 70 degrees to 111 degrees. Okay, in terms of specific heat of water. If we're going to heat liquid sodium, the specific heat is not as high as the specific heat of water. On the other hand, you can heat it a lot hotter. And if you have liquid sodium at 1500 degrees Fahrenheit, and then use that to make steam at night, then you've got a storage mechanism. That's called solar thermal, of melting sodium and storing it overnight. And don't let it get solid again, or you got a problem to pump it back up again. But since it melts at 207.9 degrees Fahrenheit, you make sure it doesn't cool off down below much more than maybe 300 Fahrenheit. So again, just looking at some possibilities for storing energy. Okay, and we're going to look at kind of what's out there, but it's all based on some of these fundamental constants that you read in the back page of your physics book, where they give you all these conversion factors. Then there's the chemical part, like lead acid batteries. You can store a kilowatt hour and get by with that with about 75 pounds of lead acid battery. If you do it with a lithium iron phosphate battery, you can store that kilowatt hour in about 25 pounds. And if you use a redox flow battery, one of the fancier new batteries, you can store a lot, but the energy density is fairly low. So they're kind of large and you kind of keep them in one place. You don't put them in a moving vehicle. So in any case, some of the perspectives. Let's look at, in terms of small photovoltaic system, because they're kind of a model for an energy storage system. I like to just lay some groundwork as energy storage, and then we'll imagine what would happen if we make something a whole lot bigger than a small photovoltaic system. Okay, and I'm going to click these kind of quickly, because what I want to do is get to a picture that shows exactly the block diagrams of the kind of storage that has been around with photovoltaic systems for a long time. And the important thing is that the electronics folks have invented some pretty nice inverters that can do a conversion from DC to AC at about 98% efficiency or higher, and that isn't half bad. If you're going to connect your inverter to the grid, you need to make pretty nice electricity. In fact, the matter is, most of the inverters on the market right now make actually better electricity than a rotating machine. So we're good there. And the other thing is, you simply have to have the inverters to keep the grid happy by not bringing it down by trying to connect in and not be able to synchronize. So the problem of synchronizing the output of an inverter, it takes roughly 3 or 4 milliseconds to do that. And so it really doesn't take very long to connect an inverter into the grid. The only thing is, the grid has to, the inverter will not start feeding the grid for 5 minutes, because it's going to monitor the grid and make sure the grid is stable before it starts feeding electricity. But then it turns on and keeps the grid happy. So in any case, IEEE 1543, 7/2003, and UL 1741 were adopted way back, and we now have IEEE 1547-2000, which is a major change to keep the utilities happy, that there are folks out there with energy storage that can help them out during times of utility peak needs. So it's all about the inverter. Let's talk about inverters just for a minute. And again, the thing about battery backup inverters is they are basically current sources. And there is a difference between a current source and a voltage source. The voltage source is like what you plug your plug into the wall, and it is basically a constant voltage regardless of the amount of current it supplies. And a constant current source supplies a given amount of current regardless of the amount of voltage it's supposed to be working into. So and the current sources, there are not very many of those other than electronic current sources. In fact, I don't think I know of any, but electronically, it's no big deal to make a current source. The nice thing about having current sources for inverters is that they can be synchronized by the waveform of the utility voltage. So these current sources are looking at the utility voltage, they're measuring the frequency and the amplitude of the utility voltage. And as soon as they find that that voltage is nice and stable, they click on in and right along with the phase of that voltage, unless the utility says, we would like for you to help us correct some power factor. And so we are going to adjust the output of your inverter so it will look more like a capacitor to correct some of this inductive current that's in our line and stabilize a bit. Okay. So when the grid goes down, though, then these inverters have to switch over, and now they act as voltage sources because they have to have a fixed either 120 volts or 240 volts, or maybe 120, 208, or whatever three-phase you might want them to have. Maybe it's 600 volts three-phase. Lots of possibilities there. They will charge batteries when the grid is operating and the sun is down. If the batteries need a little charge, they can charge the batteries. And the input to these inverters is the voltage of the battery. So the inverters themselves don't need to do maximum power point tracking. In other words, they don't have to make sure that the maximum amount of power possible is extracted from the solar array. They also don't need to do ground fault detection and interruption or arc fault circuit interruption for these inverters. But now that doesn't, just because they don't need to do it, sometimes they do it because they take on additional functions. And some of the modern ones do all of these things, even though once upon a time they were done by separate entities within the system. And of course, for rooftop solar these days, you've got to have a way to turn it off so that there is no electricity from that solar system anywhere but within the boundaries of the solar system and of the array. And so rapid shutdown is part of the inverter. And of course, they're quiet, they don't pollute, and there's lots of nice things about inverters. They save trips to gas stations and so on. And their UL 1741 compliance simply means they keep the utilities happy so they can connect in with the utility. I see a Q&A. Let's click here and see what we got. MPPT. MPPT is maximum power point tracking. There is one voltage at a given sunlight intensity where a solar module operates at its maximum power, and that for a typical module is going to be somewhere between 40 and 50. And so what the maximum power point tracking electronics does is it adjusts the voltage, it measures the power, and it adjusts it again, and they see whether the power goes up or down. And if the power goes up, it keeps going in that direction until the power starts going down again. So it simply makes sure that your solar array generates as much possible power as it possibly can, and it's all done electronically. Okay, so Jeff, hopefully that explains it, and everyone else who may have had that question. And thank you for asking the question. I taught electrical engineering for 35 years, and I always told my classes, the only bad question is the one you don't answer. You're paying good money for this. You deserve answers to your questions. You may not get them all, but they'll be honest answers. If I don't know the answer, I'll just tell you that. Okay, so let's go here again. And so there's two different kinds of battery backup systems. There's DC coupled and there are AC coupled systems. And the reason I'm clicking here is I want to show you pictures. Here's a DC coupled system right here. On the other hand, when you have the slides, if you get them, if you want to look at them, the previous slides explain what's going on here in the picture. But I thought you'd rather just look at the picture and listen to my Well, I'm not sure. My voice is not exactly that of the best tenor in the world or the best baritone in the world, but it does get words out. Upper left-hand corner, solar array, making electricity. Source circuit combiner box. Why is that? Well, typically your solar array is limited to at what voltage it can run at. And so therefore, one string of modules, say a string of 400 watt modules, may only be able to produce, say, 4,000 watts. And if you want 12,000 watts, then you're going to have 3 of those strings in parallel. 16,000 watts, you're going to need 4 of them in parallel. And so you run those strings into this source circuit combiner box. So you're running thin wires. Generally, it's number 10 wire for the electrical folks and anyone else who wonders about wire sizes. You'll run a number of number 10 wire circuits down from the roof into the source circuit combiner box, which may have either 20 or 30 amp fuses in it, depending on the system. And they're then combined. And so rather than a typical electrical panel where you got fat wires coming in and skinny wires going out, you got skinny wires bringing your power into the source circuit combiner box and fat wires delivering them to the charge controller. The charge controller is a device that does that maximum power point tracking. It extracts as much electricity as it possibly can from the array, or let's say that it enables the array to produce as much electricity as possible. And then it has the decision of whether it simply outputs its electricity, because you can see it's just a one-directional arrow coming out of the charge controller. But that electricity has a couple options. One, it can be stored into batteries until the batteries are fully charged. And once the batteries are charged, that electricity goes over to this green inverter. And this inverter is set up so that when the grid is in operation, it will first deliver whatever power it has available to the standby loads. If it has more power available than the standby loads are interested in, then it will ship the excess power up to the main distribution panel. And the loads there will sample away at the solar electricity, or this could be wind electricity for that matter, same basic idea. And so then these loads get their choice of whether they need it, and if they don't need it, then it goes back to utility. So you notice the bidirectional arrows in several of the areas here. If the utility goes down, then that link between the green inverter and the distribution panel, that's opened up. And the rest of the system operates by itself. So that means the battery backup inverter operates like a voltage source. It provides power to the standby loads, and it either provides power to the standby loads with battery power at night, or during the daytime, the PV array will make DC power, which will be converted over to AC power and sent to the standby loads once the batteries are charged and happy. All right, so that's pretty straightforward. The DC coupled system has one inverter, and it's a very versatile inverter that can operate as a current source when the utility is live, and it'll operate as a voltage source and disconnect automatically from the utility if the utility goes down. And then, even though it disconnects, it continuously monitors the utility, and when the utility comes back up again, it then waits 5 minutes, makes sure the utility is stable, and it then starts delivering back to the utility if the utility wants it. Here's the question. Let's see what we got. How do you preclude second and fifth harmonics in the green box? For the most part, they are filtered out with inductive and capacitive filters. The harmonics, generally the green box, the basic sine wave is generated with a pulse type system, but then the pulses are smoothed out to the extent necessary in order to meet the second and fifth harmonic requirements of UL 1741. And unless you do sufficient filtering on your sine wave, in your green box, battery backup inverter, or any inverter that's connected to the grid, you can't sell it. You can't list it to 1741. And utility it doesn't have any interest at all in buying it from you. So there are lots of harmonics, but second and fifth in particular are filtered out by filters, electronic filters within the inverter. Okay. So this is this so-called DC coupled system. The only drawback here, there may be more than one drawback, but the main thing is your power source, your energy source, the gray box, the PV array, or whatever energy source it might be, is way up there in the left-hand corner, and it has to go through the charge controller, maybe somewhat into the batteries, back out of the batteries, before it gets to the inverter, and oftentimes that inverter will only be 94, 95% efficient before the power actually gets to power up some AC loads. So it's not unusual to lose maybe up to 6% of your available energy in this system. The good part is that in the modern systems, the charge controller and the combiner box are incorporated in the green box, so you don't have to worry about that. So you just connect the storage battery and you connect standby loads and you connect to the utility and you're all done. I'm sorry, I missed out on connecting to the solar array. That's obviously pretty important as well. So modern systems, they consolidate some of these boxes. All right, the other kind of a system that's also very popular these days is the AC coupled system. And what this one does is the array, the DC from the array goes directly to a direct grid connect inverter, which means this inverter meets UL 1741. These are current sources, and they feed the standby loads directly at an efficiency of somewhere near 98%. If you have a little bit of loss in the wiring, then you're looking maybe a little below 98%, but those wiring losses are going to be there whether it's an AC coupled or a DC coupled. So your standby loads are powered up immediately, and any leftover electricity then is fed to the battery backup inverter. So that AC out is kind of misleading because you can put AC into there too, and not everybody realized that long ago. But anyway, that is the principle. You can do that. There is a bus bar in there. And again, that power first choice goes to storage batteries to keep them charged. Once the batteries are happy, once the standby loads are happy, any excess goes to the utility. Of course, with this one, when the utility goes down, there's an interesting, and even with the DC couple, it's interesting because, and here's a question, we'll get that in just a second, hold on. When the utility goes down, then the green inverter has to make a utility quality sine wave, which finds its way up to the standby load panel, which then the direct grid connect inverter sees that, which tells it that it is okay for it to make electricity by converting the solar DC into AC. And so that's all well and good, but at night the story changes. There's no PV electricity. The energy comes out of the storage batteries. And if that inverter, if the batteries run too low, and if that inverter then is not able to start up again because of the batteries being out, then it can't look like a utility to the direct grid connect inverter the next morning, and the direct grid connect inverter can't turn on, and then you're out of luck. So you get some interesting control functions taking place here to make sure that there's always enough electricity left in the batteries to turn the direct grid connect inverter back on again the next morning to be able to capture more DC energy from the array. All right, let's go to the question. Is it true that typical PV, that is true. A typical PV panel is only 20% efficient. Maximum theoretical limit For silicon, it's up around 27%. So there's some silicon out there that's at about 21, 22 now, but 20 is pretty typical. And what that means is of the 1,000 watts per square meter that are incident upon it, it can convert 200 into electricity. And the other 800 are either reflected away or converted to heat, 400 of which go up, 400 of which go down. But it's a nice shade for your roof, but 20% efficient. And by the way, 15 years ago, 13% efficiency was good. So you can see they're 50% more efficient now, not 7% more, but 50%. The same roof now can make 50% more electricity than it could once upon a time. So hopefully that is a brief answer. We've got a lot longer answers to that in our photovoltaics courses. Just a quick answer, about 9 to 10,000 watts is about what it normally takes to power up the annual electrical needs of, say, a 1,500 to 1,800 square foot house. So to give some idea of whether, what's out there. My sideline, actually the last year and a half, almost 2 years now, I've run plan checks on a little over 3,000 designs for residential solar, and pretty much all of these designs, people want to make all their electricity. Of course, you can't make the stuff you need at night during the day unless you save it, but they do produce over a year's time almost all of the electricity, or an amount of electricity almost equal to the amount that they use. Some of it's sold back, and they buy some at night from the utility. Again, maybe that's more answer than you were looking for, but 20% is about right for a typical silicon PV panel. Some of the more sophisticated panels that they can sometimes they have sometimes deploy them in space can get up into the 45% range with multiple layers of different just different layers with different bandwidths. But again, that gets way too complicated than what we're looking for right now. Okay, so we see that there's DC coupled and AC coupled systems. This is a basic block diagram of the system. And again, the direct grid connect inverter could very well be a single microinverter for every module in the solar array. You could very well have 40 modules and 40 inverters right up on the roof, inverters right under the modules. So you're actually sending AC down from the roof to your standby loads. And if the standby loads don't need it all, then it gets sent straight back to the utility. If you've got storage, then what you really need is not necessarily battery backup inverter in this case. You just need something that will simulate the presence of a utility grade voltage source. And if you can do that, then your PV array with its microinverters continues making electricity. All right, well, that's a little bit more detail. We do have courses on battery backup, photovoltaic system design. This is just basically a concept exercise here, so we can take a look at what a bigger system would need to do functionally. Okay, so up the simple point that all we need to do is scale up the inverters and the arrays and the storage, and all of a sudden we have some systems that are looking more like utility scale. And scaling up the inverters, arrays, and storage, it's happening in real time in a lot of different places right now. And we're going to take a look at some of the storage that's out there. There's also some more interesting things. There's things like localized smaller energy storage. Okay, and electric vehicles with smart garages. The big Tesla stores 100 kilowatt hours in their batteries, and probably only takes them maybe 5 or 10 kilowatt hours to get to work. So there's a lot of extra electricity stored in those Tesla batteries most of the time. And if they could sell some of that back to the utility, it presents an amazing amount. If we had 150 million of those on the road, that would be an incredible amount of energy storage available for the utility at 4 o'clock in the afternoon while people are parking their cars at work plugged in, so the utility can ask them for electricity if it needs it. And they're not about to give it away for free either. They will negotiate a price with the utility so that the people who own these vehicles will have their own little energy supply that they can sell electricity to the utility in the afternoon when they want it. Watch for that down the road. It's being worked on. All it takes is bidirectional inverters. They've already got that in Tesla Powerwalls. So or bidirectional AC storage, and Tesla Powerwalls already have that. So it's not that we have to waiting for the technology. We're waiting mostly now for the paperwork. Microgrids, rather than just one house being independent or having at least its own storage, you can do a whole neighborhood that acts like a house. And that whole neighborhood could be a zero energy neighborhood, meaning that the amount of internally produced energy is equal to the amount bought from outside. So there's interesting stuff. I think it's probably obvious why energy storage is important. I noticed last night when I woke up at midnight, the sun wasn't shining, and I wasn't even surprised. I kind of got used to that. And I guess I have woke up at midnight with the sun shining, but that was way above the Arctic Circle, and there are different things happen from time to time. But then again, the wind doesn't necessarily blow at 18 miles an hour 24/7 either. So you need a little extra energy storage if we're going to use wind and solar and hydro and geothermal and other renewable sources. Probably going to need some storage as backup. Okay, so you can pretty much predict the amount of energy that a wind system or a photovoltaic system will produce over a yearly cycle, but it's pretty hard to determine or to even guess exactly how much power it's going to be producing at any minute of the day, depending on whether it's clouded over or not. So energy and power, they're both important to know. And oftentimes a source is rated by how much power you can get out of it and how much energy you can get out of it. For example, a 10 kilowatt hour battery backup system will typically be capable of generating about 3,700 watts of power. And if you drain the battery faster than that, it's not good for the battery. So they have current limiting in these batteries to prevent you from draining them faster than the safe limit. Large thermal sources can benefit a lot from energy storage. See, we've been doing energy storage for 60 years. We've been pumping water uphill ever since the first nukes were put online. And they discovered that these things don't like to, once they're up to speed, they don't like to change it. They're very critical. Pull those control rods out a little too far and you get a meltdown. Leave them too far in and it shuts down. So you have to have them just right to get the right stability on that source. So they really didn't want to have to change the output power of a nuclear power plant once the thing had been properly adjusted. So since they had more power than they needed, they decided they'd build some, start pumping water back uphill again and let it come back down the hill the next morning or whenever they needed it. I'm guessing there's some folks from New England here. If you've ever driven across Highway 2 in northern Massachusetts, there's, I think, 4 or 5 sites of pumped hydro that you can have a look at as you're driving along that beautiful drive. Rotating thermal sources can follow the load, but variable sources only generate when conditions are right independent of system load. Okay, well, yeah. What do we mean rotating? This thing, there's a little more subtlety in this statement than might come meet the eye. If you have a 5,000 watt gasoline generator and you crank that thing up, and be sure to put your headphone, your earmuffs on, or your earplugs in first, that thing can generate anywhere up from 0 up to 5,000 watts. Now, the efficiency of operation of that machine when nothing is connected to it is pretty low. In fact, 0. You're still burning fuel. And the efficiency continues increasing as you add more load to it, more lights, more air conditioning, more whatever. And there's a governor there that notices that there's electrical influence on the required torque from the mechanical driving source. And then it burns more fuel to develop more torque. And that's all covered with basically putting your foot on the gas a little harder when you're trying to drive uphill. And this is the equivalent of that for the rotating thermal source, the rotating generator, gasoline generator. So they can follow the load just fine. You add a little extra load and the governor kicks in a little more gas and keeps it up to speed. And as you add more load, the frequency tends to go down, and the governor says, no, you got to speed up. So it takes puts a little more gas in order to get the speed up. But with a solar source, they generate when sun is shining, and if the cloud comes over, you can't crank any more out of it. It only gives you as much as the sun is willing to share, and in fact, 20% of that. So therefore, you need something there to act as a buffer. Okay, and so you got two choices with the excess energy from a variable source. You curtail it or you store it. And if you curtail it, that means you're just throwing it away. If you store it, you may only get 80 or 90% of it back again, but that's a whole lot more than you get back if you get nothing. So you just need to look at the economics of the issue. And to some extent, storage, again, it's kind of like curtailment, because there's some loss in storage. It's so-called round trip efficiency, and that typically ranges from 50 to a little over 90%, depending on the mechanism. And it is nice, though, to have it, because it's there. Then if you're storing it, you can generally turn it on pretty fast to give a boost to the grid if it needs the help. Why is interest in storage increasing? Again, kind of obvious. For one thing, there have been some really interesting advantages in storage technologies. For another thing, fossil fuel prices, oh, no, they wouldn't possibly be volatile. How could they be? Just because they've gone between $3.50 and $5.50 a gallon in the last 6 months or 12 months, that's not volatility, is it? Even natural gas varies in price. Ask the Europeans about that. Deregulated energy markets. Why is that? Well, because now you can have your own storage facility, and all you have to do is find somebody who wants to make use of it. Just like you can have your own transmission, your own generation. There's federal law that says if you make good electricity that's utility suitable for the utility has to buy it from you. It doesn't say how much they have to pay. That's negotiable, but they do need to buy it if you have it available. So that's an interesting issue with public service commissions and so forth. There are public utility commissions, depending where you're living. So there are also markets for high value ancillary services. And what in the world would that be? Well, that's, you have to figure out where is your most economical electricity going to come from, and how are we going to get it? And that's an ancillary service, because that involves computers and even people. They even allow people to do a little bit of the thinking involved here. There are challenges to siting new transmission and distribution lines. And so if you can replace transmission or distribution with storage, you know, I don't know how many of you tried permitting a transmission line across the Florida Everglades, but nobody's succeeded in that yet. And it may be a while before anybody does. So it could well be that there's going to be a little storage, and it's probably not going to be pumping water uphill down in Florida, not in South Florida anyway. LCOE, another one of those great acronyms that you can take home to discuss over dinner tonight, means levelized cost of energy. And this very simply means that if you add up the cost of construction, operation, maintenance, repair, maintenance, same thing, I guess, fuel, and decommissioning over the life of a system, then you take that cost and you divide it by the amount of electricity you're going to make, and then you decide what you have to charge for that electricity in order to pay for your system over the life of the system. It's a nice way of comparing different ways of making electricity. And the levelized cost of energy for wind and photovoltaically generate electricity have been decreasing extremely rapidly, to the extent that both of them are now less expensive, especially on the utility scale, than making electricity any other way that they make it. So that's why the utilities are really making, they are installing a whole lot of photovoltaics, and they realize that it's only going to make electricity during the day, but they're still building solar farms in the 100 megawatt range, realizing that they need to be dealing with some kind of storage, various ways. And I don't know, I'm not privy to what ideas they have, but I'm guessing some of the things we're talking about today may be a lot of the things that they're thinking about. Okay. And the other thing about storage is some people actually believe that carbon dioxide emissions from thermal sources is bad and causes global climate change. My goodness, who could believe a thing like that? Well, they convinced me of it. And all you have to do is turn on TV and see evidence of it. So anyway, so let's talk a little bit about, I mentioned the idea that you have to talk about power and not just, but power and energy, okay? Now, a lot of storage mechanisms, like batteries, then they have some internal resistance, and that limits the amount of current that can come out, okay? And when that happens, then you have to be careful, because if you run too much current through, you've got this, the amount of heat dissipated inside the storage mechanism is proportional to the square of the current that it's delivering. And lithium in particular, you don't want it to overheat, and that's why lithium has very sophisticated management systems built within the battery pack to make sure that it doesn't overheat. They limit the current, and they've got temperature sensors galore and all kinds of good stuff in those packages. So there is, depending on how many kilowatt hours of energy you store, the rate at which you can discharge that source is going to be the power available. And so energy sources are actually evaluated in terms of kilowatt hours, megawatt hours, gigawatt hours, but also kilowatts, megawatts, and gigawatts. Some is classified as energy storage. Lead acid battery is a good example. If you want quick power, lead acid is not necessarily a good place to get it. But it's not all that bad for energy storage, although it's kind of outdated now. It's a pretty heavy battery for a kilowatt hour, and there's not as much going around now as there used to be. Some is classified as capacity storage. And if we just use as a comparison, the lead acid battery that you would use to run an electric trolling motor on your boat would be energy storage, because you don't drain it very fast. You want that thing to run for quite a long time. On the other hand, the lead acid battery that you use to start your car is capacity storage, because you need a fair amount of power to turn over that starting motor. So it's all a matter of whether you want energy or power, and sometimes you can design the particular storage mechanism to produce one or the other. With lead acid, the thinner the plates, larger and thinner, gives you more power, more surface area. If the plates are thicker, with less surface area, then you can store more energy. So some are either energy or capacity, but some can do both. Lithium, in fact, is pretty good as providing either one. And if it's going to do that, it has to have relatively low equivalent internal resistance. Okay, if it's a chemical source. The storage capacity, for example, if you had a large flywheel, as you start extracting energy from it, it starts slowing down. And of course, if you're driving rotating generation that is directly connected to the grid, that flywheel is going to slow down. On the other hand, if you happen to take that flywheel output as and convert it to DC and then re-rectify it at 60 hertz, then you can let it slow down to 0 and make use of all the energy stored. So there's a lot of interesting options in terms of sources. And you kind of start with what is it you want to get for this thing, and then you opt for whatever source does whichever you need the best. Here's an example with lead acid batteries. You discharge them slowly, you can get a whole lot more ampere hours, which is basically the energy, than if you discharge them quickly. And again, it's simply because in the fast discharge, your ampere hours get dumped into heating the battery, whereas the slower ones, they actually get the current out of there and it does work outside the battery. So folks have actually, based on what we've just been talking about, there's basically 3 classes of energy storage. And these are the 3. One is power quality and regulation. And what that means is transient stability. Let's just say that you lose a generator on the system, a big one, maybe 100 megawatts, maybe 500 megawatts, whatever. If that generator drops out suddenly, you're going to have some significant transient behavior in that system. And it is nice to have something to stabilize that transient and to damp it out. There are cases with reactive power where you've got motors running and you want to correct for that lagging power factor with the leading power factor. There are cases where when the system gets really heavily loaded, that the frequency starts dropping. And especially if you lose a source, the frequency will go down very quickly. And if it goes too far, then you're going to start losing additional sources. So you need something to quickly bring that frequency back up again. And so we're talking about, in a matter of seconds to minutes, that you need something to be able to discharge to stabilize the grid. So that's class number 1. And the other one is bridging power. And that means providing a contingency reserve power while you're waiting for something else to turn on that can provide power over a longer time period. And that generally takes in the time frame of minutes to about an hour. And the third class is energy management. And what this means is load leveling. And it's firm, predictable capacity that's available for transmission and distribution, so that you don't necessarily have to build additional transmission or distribution lines. Instead, you borrow from the neighborhood-friendly storage energy management system. And this kind of system has to have energy available for a period for hours on end, like all night long. Okay, now here's an interesting big battery. Let's try the raise hand function. I'm kind of curious how many people have seen this before. I'm going to light up my participant box over here. And if you'll, wait a minute, why is my participant box not turning on? Here it is. Attendees, here we go. If you have seen this picture before, please raise your hand. I see that Walter and John and Jonathan have seen it. All right, but there's okay, Ryan has seen it. 4 people have seen it. All right, 5. If you've all seen it, then I don't need to tell you what it is. 6. Okay, this happens to be an interesting thing. Let's just replace, click up the answer here. It was back in 2017. South Australia was having a little trouble with their grid stability. You notice they have a significant amount of wind out there, a lot of wind power. They have coal power, a mixture of power, but they had some little stability problem with things shutting down. And so Elon Musk said, here's the deal. If I can't build for you 100 megawatts in 100 days, you can have it for free. And I don't know whether they figured, well, I will definitely do this because it'll take them over 100 days to get the permit. But in any case, in less than 100 days, roughly 90 days later, that spot that looked like the bare brown ground behind it became a 100 megawatt battery system, which means it could deliver 100 megawatts of power to the grid in a matter of less than 1 second, if necessary. Okay. Now, and since he did it in less than 100 days, he actually got paid for it. I don't have no idea what it was paid, but not too long after the thing was installed, towards the end of 2017, a coal-fired power plant tripped off. And in 140 milliseconds, this thing had been cranked up to 100 megawatts of backup power to help stabilize the grid. Because it's electronic inverter generation, so they were able to sink in and bring that grid frequency right back on up. And in the meantime, since this system also had 129 megawatt hour capacity, they had an hour and a half, roughly, well, 1.3 hours, okay, to get some other power plants online to replace that coal-fired. But in the meantime, we had 129 megawatt hours available for delivery by this system to stabilize the grid. So if you want to read a little more about it, here's some references, okay? And apparently some of the folks have. Here's a question. Let's see what we got. Which are the batteries and which the inverters? Good question. I think actually these are packaged units. I never did count them all. There's 3, 6, 9, 12, 15, 18. Oh my goodness, 60, probably at least 100 of them. So these are probably 1 megawatt packages. And it looks to me like the inverters, they look pretty identical, don't they? The inverters, I'm sure, are each one of those units, each one of those blocks probably has its own 1 megawatt inverter. That's what I'm guessing. On the other hand, what have we got in the middle? Those could be combiners. You know, I wish I knew the answer to that. I'm glad you asked. I'm going to have to try to find out now. All I know is the batteries, and the inverters are all within that within that particular fenced-in area. Yeah, wow, I'm really glad you asked that question. Now you really got my curiosity up. Oh, wait a minute. Wait a minute. The inverters must be on the inside. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But I'm only guessing. I'm only guessing, but it's all within that confine of the inverters and batteries both. Okay, just wanted you to see that because it's there, it's real, it's out there, it's in South Australia. It's a long ride to get to see it, and I have not seen it. But it's interesting for sure. And here's basically what that thing does. It during a night when there's extra wind energy in the system, it charges the batteries. And during the day when they need power, it kind of goes up and down during the day. And when they really need it, they open it up and dump power into the system from the batteries. And they can do that every single day. And again, here's a reference. Whoops, I'm going backwards. In 2017, there were a few other projects going on. So it's not that, and notice that the vanadium flow battery and the sodium sulfur flow battery were part of those projects. So even though the energy density is lower in these, they found space for them. You know, what better place than an abandoned coal-fired power plant as the real estate for a storage facility? But we're not sure whether that's where the Chinese and Japanese, because apparently Chinese haven't told a whole lot of people exactly what they're doing. And I guess they hadn't found out at the time exactly what the Japanese were doing either. So anyway, but then again, there's they also were doing an experiment with 1,000 battery backup systems all over the place, just to see how that would respond. And that total of 1,000 battery systems with a total capacity of 5 megawatts, that means these are 5 kilowatt battery systems. And the megawatt hours is 7.5, which means 1,000 of them is 7.5 kilowatt hours of storage. And that's, you know, the standard kilowatt amount of storage that people are installing right now in a small system is 10. So this is a pretty distributed virtual power plant. And I'd love one day to get some results on what they're finding out about the distributed virtuals as well as the large centralized projects. But anyway, again, just an informational thing. This is kind of stuff that's out there that's happening. And again, here's some references. How does fuel cost affect the installation of renewable sources and the installation of storage versus other sources? Well, there's clearly no fuel cost for wind and solar. Once they're in, they run, as long as the wind blows and the sun shines. So there's no, you don't have to burn fuel to make electricity with them. And that makes it pretty advantageous to try to keep them running all the time, because if you keep them running all the time with no fuel cost, then the cost per unit of electricity goes down even more. So that LCOE thing. So if you can run them 100% of the time, your LCOE goes down. So it'd be nice not to have to curtail them, but if you don't curtail the wind and the solar, then you're going to probably have to curtail your thermal sources. And then of course they use less fuel, but then they produce less energy, and that's what they sell. So that's an issue when you install all this renewable stuff. The value, the payback, the ability to pay back the investment on these other energy sources goes down because they're just not making enough electricity. So to get that LCOE back, you have to charge more per kilowatt hour. Well, you can still get by with that during peak time. If you have to charge 25, 30, 35 cents a kilowatt hour, you got to have the electricity. But if you can produce and provide that necessary electricity to keep the grid up with storage for a price less than 25 or 30 cents a kilowatt hour, then you need to start thinking about it, because that's where things head with this kind of situation on fuel costs versus no fuel costs. So anyway, this is just what we've been talking about, so we don't need to talk about that again since we wrote it down. But here's an example of one of the challenges, though. The red graph at the bottom is the actual energy production. Actually, you could call it power production or kilowatt hours per hour, kilowatts. And it's over a period of about 160 hours. So you notice that there are times when the wind is blowing pretty hard and the windmills are kind of peaking out around 5,000 megawatts. And then you've got your load up there, the green. And without the red, the blue would be right on top of the green because all the green would have to be provided by the blue. But when you add the red, then the blue only provides the amount shown on the picture, and that all looks well and good, except there's one interesting challenge here. And if you look at, say, the slope of the blue line and the slope of the green line, right around 55 kilowatt hour or 55 hours, you notice the slope of the blue is much steeper than the slope of the green. And the reason for that is because all of a sudden the wind is going away. So that means the conventional has to make up for the loss of the wind power faster than it would have had to simply follow the load. And that's a challenge. So what do you do about it? Well, you add some storage and let the storage help take care of this bigger slope. Again, here's some more pictures back in 2011, a long time ago. This picture was part of that renewable energy futures study, and it took into account a lot of different types of generation. Here's what they are: compressed air, double layer capacitors, flywheels, lead acid, lithium, then on down the line. And if you look at the picture, it tells you how much power you can get from one of these and how long you can get that power. How long does it take to discharge? So you look at this EDLC, double layer capacitor. Wow, you can get a megawatt from that, but you get a megawatt for 1,000th of an hour. So that, that's one of those things that will maybe help stabilize in an instantaneous fashion, but it's certainly not going to do you much good if you have to have it running for a long time. Zinc bromide, nice little chemical technology. They'll give you an hour's worth of power at a megawatt or so back in 2011. But it's interesting to just notice the one thing, the lithium ion back in 2011, the power, rated power versus the discharge time. And then take a look about the orange in the hexagon over there, because that's where the 2017 Tesla lithium battery was. So are things improving or what? Instead of having 1/10 of a megawatt for less than an hour, you're looking at 100 megawatts for more than an hour. So, and folks are scrambling with every technology out there to try to go up to where the pump storage hydro is. And you notice that's the biggest of all. You can have 1,000 megawatts for 100 hours with pump storage hydro. And that's why that's the major storage mechanism in the world today, by far, is pump storage hydro. May not realize it, but it's out there, and it's out there big time. But it takes about 10 years to permit and complete a pump storage hydro system, and people are now starting to cancel plans for them because they're looking at other technologies coming up. So stay tuned for what happens here. But here's what was there back in 2011, and it's all moving off up to the upper right of the curve. All these various technologies are trying to push them up off to the right and upward to get more time and more megawatts. Round trip efficiency is simply You need to be sure you compare your energy storage sources apples to apples. Because if you're charging your battery in your car, you got DC in and DC out, and you decide how much DC do you get out for the amount of DC in. But if you're doing, say, a Tesla Powerwall, you're charging it with AC power going in, and you're discharging it with AC power coming out. So you have to rectify it into DC to charge those lithium batteries. And on the way out, it has to go through an inverter to make AC. So the only fair way to compare storage mechanisms is the AC in versus AC out comparison. So if we do that, if we do the AC round trip efficiency, then we get the following numbers. For batteries, AC to AC, around somewhere at 70 to 90%. For pumped hydros, somewhere at 70 to 80%. For compressed air, somewhere 50 to 65%, flywheels 60 to 80. And this is data from the Interstate Renewable Energy Council, a very reliable group who has been following in operation for a little over 20 years now, and they are very good data people. So if you want looking for good data, Google IREC and see what kind of reports they've got. They've got some pretty good stuff out there. Here's a picture of your standard pump storage hydro. No particular surprise. The interesting thing is if you're letting the water run downhill to generate electricity, you can reverse the process. It takes roughly half an hour to go from pumping water uphill to flowing water downhill. Okay, and the quantities of water involved and the heights, you got the numbers, the formulas up the beginning of the set of slides, so you can figure out exactly how many gallons say 100 megawatt pump storage hydro plant, how much water that involves. It's very interesting to do that. It's almost worth skipping a TV show episode, but not totally necessarily worth that, but it's almost certainly any boring moment when you want to do something totally fascinating, do that calculation. These were, as I pointed out, great for pumping water uphill at night to save the nukes that night when nobody needed that electricity. Well, at least it all wasn't needed, some of it was. But now you can pump that water uphill any old time, because if you got excess wind or solar during the day, pump some water uphill. That's fine. That reservoir is plenty big to pump a lot of water uphill. And then let it come down when you need it during the day. You can anticipate a lot of times about a half an hour advance that you need to now start running the water down the hill. So this is why pump storage hydro is so popular and so effective. You can do this cycle tens, even hundreds of thousands of times. So little maintenance on the pumps from time to time and on the system, but it's pretty reliable. And a lot of the system's been running now for 50 years. Here's some costs again, just for numbers reference. And you can compare these pump storage hydro costs with other systems. This is only up through 1985 because they haven't been making very many of them since 1985. These are all in place in order to use all the nuclear that was so popular up until it started becoming more expensive. So round trip efficiency is between 50 and 83%. And of course, that round trip efficiency is going to be part of the factor you incorporate in your financial decision making. If it's less efficient, then it better be less expensive to build as well. Otherwise, you're not coming out very well, and you might want to think about something else. Where are they? Well, here's where a bunch of them are operating, and there were a bunch of them proposed in 2010. By now, probably some of those have been canceled. But obviously, in the mountainous areas, you don't see much down in Florida, Louisiana, Texas has a little bit, not much, nothing at all in the Plain States. Get out in those mountains though, and there's a fair amount of pumped hydro that people still can do if they want to. Again, permitting is an interesting challenge. Where are the stored hydros? 27% in China, 19% in Japan, and another 19% in the United States. Can you imagine that? Japan is not really anywhere near as big as the United States, including Alaska, and yet they have the same capacity of stored hydro as the United States. And in proportion to the number of kilowatt hours and gigawatts they use, it's huge. 35% to the rest of the world. People talk about being totally on renewables. Look up Costa Rica. They are as close to being 100% renewables down there because they've got lots of wind, lots of hydro, and they're building PV, and they tend to be very efficient buildings as well. They may not be lighted terribly bright, but they don't use as much electricity per capita as we do either. So a lot of these things, interesting, you say, oh, nobody else is doing it. Well, okay, guys, that's not quite true. We've got 1/5 of all the stored hydro in the world, and the other 4/5 is elsewhere. So let's don't blame the other guys. Let's start looking in the mirror and start thinking about what we need to do here. Growth of pump storage hydrogen or any bulk storage. See the little orange hats on them? That's compressed air. I guess that's red, but it looks kind of orange depending on your computer screen, I guess. So compressed air storage capacity is a whole lot less than pumped hydro. But in terms of megawatts, 20,000 megawatts, that's a lot. So a lot of the storage we're going to need is already there. And that helps to have a head start. So what about additional pump storage hydros? Well, here's a little information on some proposed stuff out there. This is more recent. This is between 1960 and 1990. But whoops, I should have backed up. But the more recent ones are looking a little more expensive, and people are taking a second look to see whether there's other things they might want to do. There is a lot of, by the way, REEDS, another nice acronym to use at the dinner table, Regional Energy Deployment System. Okay, and no surprise, the resource potential for stored pumped hydro out west, particularly in Utah, it's amazing. Of course, they've got some really neat places out there in Utah to pump water uphill. California and so forth, and New Mexico. So anyway, lots of places there. Here's a question. Let's see what we got. I hope I haven't waited too long. How significant is operation and maintenance? Well, let's put it this way, Chris. If it were too high, they would shut them down. So, I mean, what have you got? You got pumps, and you've got pumps in a regular thermal production facility. You've got all kinds of circulating pumps for cooling water and so forth. And you just talked about huge pumps that you have to maintain. You need to make sure they're clean and so forth. But for the most part, they're motors. And if you talk about maintenance on, say, an electric car versus a gasoline engine car, maintenance on gasoline car is a whole lot more than on an electric car, because there's a whole lot more moving parts to worry about. So I can't give you any exact numbers, but I guess probably one could Google that and come up with some number. But once they're built, they're relatively inexpensive to operate. And I think we may even have some information coming up. I'm getting old and I can't even remember what's on my own slides here. So let's see, maybe we do have an answer for you coming up. Good question. Let me say for sure that's a good question. Um, so let's see what we got here. Oh, if you want to do compressed air, this is basically the schematic for a compressed air storage. And the advantage of compressed air is that the footprint above ground is relatively small. You just need a good limestone cavern or something that has good solid walls where the air will not penetrate through and just lose your pressure. It has to maintain that air pressure. The other interesting thing that tends not to be thought about, but scuba divers have experienced it, when you go to get your tank filled, they put it in a barrel of water to cool it as the air gets compressed and put in that tank. Otherwise, it gets really hot. And of course, then the opposite happens when the air comes out. It comes out cold. So if you have a system there where that compressed air comes out and runs that turbine, that generator, and you've got some heat exchange that you need to deal with, simply because of the colder air coming out and the hotter air going in after being compressed. But then you notice the efficiency we mentioned earlier, somewhere between 50% and I think it was 80%. And so here's a place where you might find it. And the turnaround time is about 30 minutes. That's pretty good. That's comparable with the pump storage hydro. And it's about 50% faster than you can do to crank up a gas turbine engine. So that's another nice feature, that how fast you can turn your system on is pretty relevant in terms of the need of the system, of the utility system. A little more on aquifer storage caverns. This is what you'd like to have. Again, you can read that. I'm not going to read it to you right now. No need to, because if you really want to know, you'll just download the slides and digest it a little bit. I need to look at my clock, see how we're doing. 3:23. Okay. And surprisingly enough, there are quite a few compressed air sites where you can store compressed air. And notice porous rock. Isn't it interesting that you might be able to store it in porous rock? And as long as that porous rock has some solid rock around it, so that that you can actually contain the air and get it back out again. There's quite a few places there. And bedded salt, even Florida has got some of that. And the salt domes, of course, they're the ones we hear about, that they want to store the strategic petroleum reserve and so forth. That's in salt domes, and Louisiana is one of the favorite places for them. And from this picture, it's pretty clear why Louisiana would be pretty popular for salt domes. All right, so again, just some maps. $900 a kilowatt. Bedded salt, $1,050 a kilowatt. Porous rock, $1,200. So the dome salt is the preferred, and up in there in the Texas, Louisiana, Mississippi area. And so that's where most of those storage systems are. Some more numbers. Here's a question. Again, the components. Here's what you're getting up to 100% of your total cost in dollars per kilowatt. $774 per kilowatt construction for a CAES system. All right, let's see who's got a question here. BJ Segrist, what are the typical storage pressures for compressed air? Boy, you guys are good today. You asked all the hard questions. Good question. I know that they're looking at, let's just compare it with compressed air for a scuba tank, something like 2000 PSI. And when we're talking about the heat exchangers, my guess is we're probably looking in the neighborhood of 2,000 pounds per square inch. And that's my best guess. And it's another thing to Google. And if anybody has another computer or one way, or get somebody else sitting in the office next to you to Google what's the storage pressure for compressed air, please come back and let us know what that is. You've got coming up with questions that nobody's ever asked before. I'm really glad you did ask them, because the next time around that I give this, I hopefully will have the answers to them. So again, I thank you for asking. I wish I knew. I'm guessing ballpark 2000 PSI, typical to the stored air in a, now that's pretty tough steel that's containing that compressed air in that scuba tank. And I doubt that it's more than 2000 PSI. You probably got some pretty tough rock to contain that air as well, though. So I'm going to go with 2000 as a rough guess. Okay, those delays are my clicking my little boxes so I can see the slides again. Okay, next, what's some of the stuff that's coming up that we don't see out there commercially yet? Well, flywheels. Well, actually, they're out there. There are some 1 megawatt flywheels in operation right now doing frequency regulation type work. There are also smaller flywheels out there that people are using as uninterruptible power supplies, like for your computer. Not so much anymore with the computer, because most computers already have batteries like a laptop, the one sitting in front of me here. Let's see, here's another question. Oh, okay. Here's a, all right, let's see if I can click on that. See what we got. Basics of underground natural gas storage. What does it say? You know what? I'm not sure whether everybody can see the Q&A, but if you can see the Q&A, the anonymous attendee has clicked on us, a United States Energy Information Agency website that talks about natural gas storage underground. All right. And I don't have time to read it, but here it is. You can see the picture. I think you can see that on your screen. I don't know. Anyway, whoops, I did answer it live. Yeah. So thank you for that. And if you maybe would also put that up on the, that one would be worth putting in the chat box, because I think everybody can see what's in the chat box. And if anybody wants to copy that down. Okay. Now, how do I turn this off? I don't know if you can see the EIA. I need to turn that off. I guess this is it. Now I'm there. There. I'm still sharing. Okay, here we are. Wow, got me scared there for a minute. I thought I lost. It says I'm still screen sharing, and I guess I am still there. Yeah, okay. My fear is that I may click something that will close me off out of the webinar, and that's pretty embarrassing to do that. Capacitors, very fast for transient voltage stability. So we've got stabilizing frequency, stabilizing voltage with capacitors. The electrical engineers will appreciate that. You see the half CV squared, the voltage across the capacitor cannot change instantaneously. I don't know how many times you've heard that, but I'm guessing I probably said that several thousand times in the various classes I've taught. So it's a, capacitors are great for transient voltage stability. Superconducting magnets. That's one of the other formulas, 1/2 Li squared. The inductance of the magnet times the square of the current. Great for transient current stability. The current in an inductor cannot change instantaneously. All right, all this stuff that you learned in electrical engineering thought was useless. all of a sudden is becoming useful. High power batteries. Well, you saw that. Yeah. So, but there's some other stuff out there that people are looking at that's not on the market yet. And electric vehicles, that's an incredible, incredible opportunity. If you imagine the amount of kilowatt hours and kilowatts you can get, let's say it's not hard to discharge an EV at a 10 kW rate. And you can do that for an hour, and that's 10 kilowatt hours out of the 50 to 100 kilowatt hour electric tank of that vehicle. And just imagine that coming out of close to 200 million vehicles and having it available to help back up the electric grid. Of course, they're not all going to be available at the same time, but if 25%, if all, not all 100 million vehicles are on the road at the same time, most of them are still parked, thank goodness, or we'd never be able to go anywhere. We'd just have a parking lot in the middle of the road. And hydrogen is also, people have been working on hydrogen for a long, long time. And the problem with hydrogen is simply the low round trip efficiency of the electrolyzer and the efficiency of the fuel cell. But hydrogen has a higher energy density than air. And therefore, hydrogen is still considered a viable storage mechanism. And we'll probably be seeing, I don't know, a friend of mine at the university here in town has been working on hydrogen for a long time, and he hasn't given up on it yet. Let's look at a question. Where did I go? Oh, okay, yeah. Thank you for putting the website on the chat box. That's what was getting my attention. Okay, so the website now for the compressed natural gas it is now up on the chat box. Okay. Then there's the weightlifting thing. And at the very beginning, I mentioned the weight of a cubic foot of concrete because there are cranes in Europe now that have been built to lift concrete weights. So when there's excess electricity, they lift up these concrete weights, pile them up, and when they need electricity, they grab those weights and let them go down to ground level again. And in the process, it reverses the direction of the motor generator on the crane, and it adds electricity to the grid. And that's the one thing I wanted to add to the slide set. And I guess I was looking for some other things, and then I ran out of time, but maybe next time I'll have that. But I think if you go online and just say European weightlifting, there's even a name for the technology. The thing is, they are almost in the commercial stage in Europe with these things, lifting very heavy concrete, which is relatively inexpensive, to a relatively high level. And if you put it in a building, then you don't have to see the cranes. It's just a big tall building, a lot like a water tower. I think I'd kind of like to have one of those down at the end of my block where I could see it and appreciate it without having to cover over it. I think that'd look kind of neat. Anyway, numbers. Okay, you were asking about cost of various things. So here's a lot of numbers. And there's no way I'm going to be able to go through and try to go through all these numbers, but I encourage you to skip down to this slide and the next one. And there are lots of cost figures in dollars per megawatt hour of storage for a lot of different kinds of systems used for a lot of different purposes. Okay, so again, you can go to these two slides if you want some of this kind of information. And again, it's a lot let's see. Oh, okay. David Harrison, there's a YouTube. So there's another good website to watch. Thank you very much, David. Uh, keep an eye on the, now what I'm not sure is maybe it would be really nice, since the host has all of our email addresses, if there's any way that you are saving the chat box information, if you could send that by way of email to every participant, the websites that the people have been mentioning, that would be much appreciated, Mr. Host. And I'm not sure whether it's possible, whether the technology is there for that, but it certainly would be a nice thing to be able to have that. Otherwise, if you can quickly copy and paste while the chat box is still there, take advantage of that as well. Okay, so here's the Lazard's levelized cost of storage analysis, and Lazard loves to analyze energy, all different kinds. So they you know, these analyses depend a lot on the assumptions you make. And so whenever you read any of these numbers, also try to make sure you know what the assumptions are. What's the duty factor, duty cycle? Is this thing being used at 80% of its capacity, 50% of its capacity? Because all of that affects these numbers in terms of the cost of the systems. Here we have another item in the chat box. Okay, PDH source, yes, they will send. Thank you, Hisham, much appreciated. Yeah, these look like some very interesting sources. And I'm sure I'm not the only guy who's going to want to see these. So thank you. We appreciate that. An extra bonus to the session today. Thanks to good questions. And we hate to give up on coming up with good answers. And even when you help us, we appreciate it. I don't know if you can get a discount for that or not. That's between you and the boss. Anyway, these Lazards are here's again, there's a reference for it here. This came out December 19 of 2026. Okay. There's a number of different lithium technologies fairly heavily in use. There's 6 of them here. And again, if you're interested in the different chemical lithium compositions and what they're used for, here's a nice table. Again, perfect dinner time conversation. I can't imagine anything more interesting to the general public. And if you really want to go crazy over that dinner time conversation, here is a huge battery technology comparison that answers a lot of those questions about what's the internal resistance in milliohms per volt of lead acid, nickel, cadmium, nickel, metal hydride, cobalt, manganese, and phosphate lithium ion technologies. Again, I can't read all this, but you can read it if you digest it. And if you're interested, you just, here's a very nice table for you to have a look at. All right, and another really important consideration is how much space does it take to save all this energy? And so here's a nice picture that shows you how things are crowding for that upper right-hand corner again, which is, of course, the good corner of the graph. And the closer, and this is only up to a little over 2000. And I'd love to get another picture of this graph and see what it looks like in 2020, but I'm guessing it's probably more or less linearly increases straight on up towards that upper right-hand corner. And this is energy storage density in watt hours per kilogram as it has increased over the years. And look at those capacitors between 1960 on up. Wow. Really, really. And the nickel cadmium's not doing bad at all. And lead acid, actually pretty high. And lithium, they're all crowded together up in there in terms of their watt hours per kilogram. And it didn't used to be that high. And notice also it's a logarithmic scale there on the left-hand side. That is not a linear scale. So if it's a straight line on the right-hand side, it's increasing. I mean, if it's a straight line on the graph, we're talking about exponential increase here. Chat box, click on it. What do we have? Oh, I think if you can send them both, send the YouTube link and the gas storage link, because I have a feeling the YouTube link might be a pretty interesting thing that may not even be on gas storage. Yeah, if you can send them both, that'd be great. Okay. So again, if you look at the what's going on here in that little box that goes from 1900 up to 2000 in terms of watt hours per kilogram, all of a sudden, and there's your exponential, because here it's let's see, 50, 100, 150. Yeah, okay. So you've got your linear vertical axis in that box, and it shows clearly that the watt hours per kilogram has been increasing exponentially since 1900 and really grown like crazy since around 1980. And that was before people were very concerned about global warming, but they were still thinking, gee, it'd be nice to have some good storage, I guess. Okay. And the costs have been, watt hours per dollar storage costs have been increasing. Now, that sounds kind of funny, doesn't it? But what it's really saying is that for the dollar spent, you're now getting more watt hours. So the dollars per watt hour have been decreasing. So therefore, the watt hours per dollar are increasing. I might have tried plotting that a little differently, but still, the point is being made that progress is almost the old General Electric saying, progress is our most important product, or whatever it was, something like that. And again, just to put it in perspective, the little green diamond there is the Tesla at 2.15 watt hours per $2005. And in 2007, the Defense Advanced Research Project Administration goal was 10 watt hours per dollar. So 2.15 hasn't quite made it up to 10, but we're on the way. And notice that some of these actually do have 10 watt hours per dollar, but they're a little bit bigger and heavier and bulky. And so therefore, even though the storage is cheaper, there are other disadvantages to it. Okay, so we now I'm going to come to my clock here, and let's just check on the time, 3:44. Okay, so now with what we have, let's take a look at possible storage scenarios for meeting the 80% renewables by 2050. In other words, how much storage are we going to need, depending on what happens on the political scene, the regulatory scene, the research scene, and so forth. The worst situation is the constrained flexibility. That's where there's a whole lot of institutional constraints about deployment of wind and solar. The neighborhood association won't let you put your solar on your front roof, and you're not allowed to have a windmill in your backyard, and whatever the case may be. Down to the 80% REETI, ETI meaning evolutionary technology improvement. Now, I don't know if there's anybody, we got a group of at least 30 people here. And has anybody seen anything other than evolutionary technology improvement over the last 40 or 50 years? I mean, wow. So I don't see any reason why we shouldn't expect to see that over the next 50 years or more as well. So if we can consider that 80% RE evolutionary technology improvement scenario, then we want to figure out, okay, if that's what we do between now and 2050, how much storage will we actually need? Because then we can start doing dollar and cents, because we already know what it's costing for some of these. And we assume that just like with wind and solar, the costs have been coming down rather than going up like they have for gasoline and natural gas and a few things like that. Then let's take a look and see what the result would be under these various scenarios. All right, and if we do that, the constrained flexibility would mean we need a whole lot more storage, 152 gigawatts of storage. And this is, gigawatts, not watt hours, but gigawatts. But it's related to the gigawatt hours, and each technology, the ratio is slightly different. Here's a question. News on fusion research. Jeffrey, I'm not going to rule it out. I haven't seen any news on it. It has not made the front pages as far as I know. But that's certainly an interesting possibility, isn't it? If all we need to do is figure out how to contain a reaction that's at something like 20,000 degrees Kelvin. And that's the problem they've had with magnetic mirrors and all kinds of things they propose. And they're thinking of making it a little smaller scale now. I don't know where we're at. The thing is, I'm 79 years old, and I've been hearing about nuclear fusion as the be-all, end-all for the last 50 years or more. And so I'm not holding my breath. But it certainly would be a nice solution. There have been a few, the cold fusion thing that happened out in Nevada a few years back turned out to be a little bit of fake news. Jeffrey, if you've got some information on fusion research, share it if you would. But like I say, I'm not ruling it out, but it's simply not on the books as showing as currently financially viable. But again, we're talking about this the ETI scenario, and that could include fusion research. Could very well conclude some fusion becoming available, as well as hydrogen fuel cells. I mean, hydrogen fuel cells have been around for a long time. It's just a matter of how cost effective they are compared to the other sources. And that's the bottom line of what gets jumped on and what doesn't, is the cost effectiveness of it and the life cycle costing. Let's see, have I answered any questions yet today? You guys are really something. I'm amazed. You're coming up with the best questions that I've seen in a long time. And you give me a lot of homework I have to do. So anyway, isn't it interesting, though, that we're going to need 50% more electricity if we're constrained. I mean, it's 50% more storage measured in gigawatts. So in other words, power. And that probably means if we got 152 gigawatts, that may be something like 100 gigawatt hours of storage. And that's a lot of 10 kilowatt hour batteries. On the other hand, if you take 100 million 50 kilowatt hour batteries in automobiles, then all of a sudden you're putting a pretty big dent in that 152 gigawatts. But in fact, it's probably only going to be 100 that we need, according to the REFS. But then again, that's for 80%. So multiply that by 1.25 if we're going to do the 100% scenario. And it is still the kind of money that's out there compared to what normal government spending is on things like the military and compared to the gross domestic product. There's two questions. Let's see here. Okay, here's some fusion technology. So, and some more fusion technology. So, Mr. Host, if you can add these as well, that would be terrific. That way I can answer all these questions myself next time. Okay, so it's interesting, though, that what technology will do for you. just the fact that as long as you let it go the direction where people are interested and willing to put money into it, it means that the amount of capacity that we're going to need is going to drop down. And that's, in a way, that's kind of encouraging, isn't it? Oh, okay, we got Q&A now. Let's see, what do we, oh, okay. Would you type these URLs? I don't, let me ask again the host to please let us know whether you are able to get the information off the Q's and A's for including in that email. Otherwise, we would want people to type them into the chat box. And here's the chat, so maybe that's our answer. Okay, all right, so good. Right, okay, so it's all right wherever you put them. Although if you put them directly in the chat box, then our host will see them and he will copy them into the email that will go out after the program is over. Okay, so let me go back here and do this. And just keep up with who I am. Okay, so this to me is pretty interesting. And when is it going to happen? And look at this. It is happening. And look at what they're predicting. This was predicted back in 2012, by the way, that by 2022, they were going to be going big time investing in storage. Now, again, I don't have the updated information on this. I need to update this, but it's interesting just to see what was predicted in 2012 and what they think is actually happening here. But they were predicting the decade between 2020 and 2030 was going to be big time on storage. And from what I see, it is becoming big time. I need to look up the numbers, and you all might want to do that same thing as an update. But again, this is intended to show you what's going on. Not necessarily all the brand new numbers, but things are happening. Things are happening in energy storage, and who knows? Cumulative capacity in gigawatts, notice this goes up to 150 by 2050. So this is something we can track on an annual basis and probably find out whether we're on track or not. So where are we going to put all this storage capacity? Texas, of course. But these are the states where storage would be deployed in the constrained flexibility scenario. If we take away that constraint, then who knows where it might be. I need to turn that off. Okay. So here's, again, how much land do these things use? Because I know you're all been wondering about that. So here's an answer to that. Sodium sulfide batteries, about 211 square meters per megawatt. And when you get down to the lithium ion, you're at 100 square meters per megawatt. That's pretty small. That's pretty compact storage when you think about it. You can look up how many square meters it takes for a megawatt's worth of nuclear generation, but that might be interesting to look up as well. On the other hand, it's cheaper to build 100 megawatts of lithium ion storage than to build 100 megawatts of brand new nuclear power. Not cheaper to fix the old ones, but to build the new ones, it's pretty expensive. So, and I'm not speaking in favor of or against nuclear power, that others will make that decision. This is merely an assessment of what's out there and what might be coming. Water use. And, you know, compressed air and pump storage hydro, well, all right, compressed air, you got to do some cooling. So that's 0.2 of a gallon per kilowatt hour and 0.3 of a gallon for makeup water in pump storage hydro. So it evaporates. So it does use some water. Okay. Solar and wind just don't use a whole lot of water. Solar uses a little bit. Sometimes you need to wash them off. Wind, I'm not aware that wind technology requires any kind of water. I'm not sure if the blades get a little dirty. I don't think they get dusty like the average ceiling fan blades. So anyway, what are the barriers here? Well, batteries, compressed air, pump storage. Again, there's no need to read all this stuff. Just know that people are thinking about it. We got 5 minutes left. So let's move again. And here's some more barriers. And notice that pump storage hydro, the environmental and siting is one of the big time issues. But these are just the workarounds and the work that's needed to be done in order to make these various things happen. Okay, and this is where did this come from? This must have come from. I didn't even notice the reference. IREC, yeah. The IREC has got a lot of good numbers, and these are pretty recent. Summary of storage characteristic between lead acid and pump storage hydro. Yeah, I think this is one of the questions that was asked earlier. So here's a lot of information: round trip efficiency, discharge time, how long does it take to build? And notice the pump storage hydro 5 to 15 year build time compared with 6 to 12 months for lithium ion or flow batteries. Even a flywheel still is taking 1 to 2 years to build. So some of them take longer than others. Operating costs, and okay, how much was there is your question. What's the cost to operate a pump storage hydro? Obviously, that includes maintenance, and it's low, very low. So I guess I was right on that answer. I was a wild guess, but pump storage hydro is one of the least expensive long-term maintenance operating cost storage technologies. Okay, so again, here's your numbers here. So those who are wondering exactly how the operating cost of sodium sulfide flow battery compares with compressed air, well, both are moderate. Okay, so now we know. How do you charge for your storage? You know, I mean, I'm going to store a certain amount of electricity, and I'm going to make it available at convenient times for the utility when they don't have electricity from other places. So how do I add it all up? Well, one is energy time shifting, because what's energy? Kilowatt hours means you have kilowatt hours available at another time. Peak demand is big time, because peaking electricity is very expensive. So you got to include part of the fact that it's reducing peak demand has to add into its dollars per kilowatt hour price that you're charging, or cents per kilowatt hour charge that you charge for the electricity you get out of your storage. The fact that it increases the reliability and resiliency of the grid, that should be worth something. And it should be something the public utility commissions will look at when they're saying how much, whatever Long Island Electric can charge for that big storage plant you're going to build out in Huntington or where else they might going to build it. Then there's the congestion relief on the grid by having storage locally so that you don't have to pipe stuff in from far away, or you know, distribution or transmission stuff in from far away. And what about the guys and the equipment, the computers that are measuring all the stuff in the blue and the violet and the light blue and the orange boxes, so that they can optimize those boxes? That service must be worth something. So again, this is the fun that's going to happen on the regulatory side and on the utility side. And I can imagine the hearings that are going to go on at a public service commission. on exactly how many cents they're going to allow for each of these colored boxes. The IREC Foundation is doing some things to advance energy storage. And here are some of the things IREC is doing because they think it's important, and I happen to agree with them. And so, again, I hate reading slides to people, but I am happy to provide information on slides that other people can read. So I'm going to just leave this one for you to read. Know that it's here in case you are looking for some of these, some of those answers. Now, here is the microgrid that I had talked about at one point, and this basically says we're going to build a substation, and within the realm of that substation and its distribution system, we're going to have a bunch of loads. This building's going to be there. We'll have some gas turbine engines, maybe, for fast startup to make electricity when the wind isn't blowing, but we're going to have wind if it's a suitable area for wind. We'll have solar, and the mix of wind and solar will depend on the mix of wind and sun. We'll have some fuel cells, maybe. I happen to know that the advisor, the PhD student who drew this picture, happened to be doing research in fuel cells, so naturally they got added. Energy storage units, you know, whatever that we've been talking about, and even maybe some diesel generation in a big energy management center to provide those ancillary services so that this entire system can be optimized. And you can see there's a lot of information flow there in order to make the energy flows optimized. And if you include pollution and other items that don't have a price on them right now, if we put a price tag on them, that can all be taken into account by the Energy Management Center. So the whole concept of microgrids, they are building these down in the islands. I'm not aware of any within the continental United States, but I wouldn't be surprised. There must be some. I don't find out about everything that's going on. You know, I guess if one were to Google this about are there any microgrids? The only thing is you have to be a little careful here because the National Electrical Code defines a microgrid as what you got in your house if you get cut off from the main grid. So there are more than one interpretation of what is a microgrid. But here's the objective anyway. So guess what? We are done here. There's a few pictures here you might be interested in. Here's that pump storage hydro. You can imagine how difficult it is to permit that. And up on top there, that's one of those big megawatt sized flywheels. And down here, we've got some lithium batteries. And over here, we've got some flow batteries. And why do we know they're flow batteries? Because the liquid in the flow batteries, you don't particularly want to get on your shoes if you have a leak. So you have a little walkway around them. So anyway, if there are any other questions or comments, it's 4:04. I went over by 3 minutes. I apologize for that. There's a chat. Let's see what we got up in chat. A couple more websites here. Yeah, hydro is great. Again, hydro is great until, and that's absolutely right. And especially if there's a nuclear plant downstream from a hydro. Just some very interesting things. I'm not trying to sell hydro here, by the way. I'm just telling you that's what's out there right now. So thanks for sharing that. I appreciate that. Okay. So, oh, there's one new message down here. Yeah, okay. If you've got questions on the program, admin@pdhsource.com. Okay, and you can read, I encourage you to read through what's in the chat box right now. And I see one more Q&A up here. Let's see what we got. And PDH is typing that, yes, the presentation is available along with the slides. So that's why I went through some of the slides quickly, because I know that you can get them. And feel free to use them for whatever you want. I happen to have the copyright on them, and I created these for people to use and to learn from them. And that's what I do, as I try to get people to learn. Thank you, John. I'm assuming, based on your comment, that you felt it was worth the afternoon. And of course, you get your 2 credits toward your renewal. That's always nice. I'm not sure what you all have. I've got 18 credits I need to do, and I decided to do those earlier in the summer when things weren't quite so busy. But I'm glad you chose these as 2 of those credits that you need. Okay. So, Mr. Host, I believe we are complete here. Oh, one more chat. Let's see what's the chat. Charles says thank you, and I say thank you to all of you for your attention, and I particularly say thank you for the terrific questions and for the Googling you've been able to do. And I am going to do my best to Google all those answers myself to make sure that the next time I can answer more quickly. Thank you again. I'm going to stop sharing now. And click the red button. Wait a minute, let's see. Okay, this is really good. Let's see if I can copy all this.